Buenas tardes, señoras y señores. Mi nombre es Francisco Pradas, investigador del Instituto de Física Teórica de la Universidad Autónoma de Madrid y del CSIC. Y es un placer esta tarde presentaros al profesor Simon White, director del prestigioso Instituto Max-Planck de Astronomía de Múnich, Alemania, desde el año 1994. Simon inició su carrera investigadora en Cambridge con un doctorado dirigido por el profesor Donald Lindenberg sobre la formación de cúmulos de galaxias. El profesor White ha recibido numerosos premios y reconocimientos a lo largo de su extensa carrera, algunos de ellos muy prestigiosos, como la medalla de oro de la Royal Astronomical Society, el doctorado honoris causa por la Universidad de Durham y recientemente el premio de la Fundación Gruber en Cosmología en el año 2011, junto con sus colegas Mark Davis, George Eftasio y Carlos Frank, con quienes trabajó durante los años 80 en la Universidad de California en Berkeley. Por este trabajo, el cual recibió este premio, permitió validar la teoría de la materia oscura fría para entender la formación y crecimiento, y el crecimiento de estructuras en el universo. Este trabajo también demostró el poder de las simulaciones cosmológicas como herramienta para contrastar las teorías con las observaciones. Hoy en día, prácticamente en astronomía, en cosmología, todos los campos usan estas simulaciones cosmológicas que son una herramienta fundamental para el estudio del universo, en particular para el estudio de su origen, de su evolución, para ver cómo se forman las estrellas, las galaxias y finalmente los planetas, como es el caso de la Tierra. Esta materia oscura fría es un componente esencial en nuestro universo y su presencia es fundamental para entender el proceso de formación de estructuras y de galaxias. El profesor White ha participado también activamente en la misión espacial Planck, que recientemente seguramente habéis podido comprobar los resultados que ha difundido la prensa, donde se ha demostrado que esas simulaciones que inicialmente fueron las que predecían la formación de estructura que vemos en la actualidad, pues son realmente útiles para explicar y consolidar el modelo cosmológico estándar. He estado pensando en algunas palabras para describir su trabajo, enumerando muchas de sus contribuciones en las revistas más prestigiosas a nivel internacional, pero quizás he pensado en algo más sostenible, algo que perdure en el tiempo y que describa el trabajo de Simon en el futuro. Y creo que lo podemos describir como un pionero en la teoría de la materia oscura fría que explica la formación de estructura y galaxias en el universo. Finalmente, me gustaría destacar también su legado académico como profesor. Simon ha dado clases tanto en la Universidad de California en Berkeley, en Arizona, donde también fue profesor, y en la Universidad de Cambridge y, por supuesto, en el Instituto Max-Planck, donde actualmente pues, realiza su trabajo desde el año 1994, como antes he dicho. En total, ha dirigido 35 tesis doctorales, que, como podéis imaginar, pues, es un legado enorme. En la actualidad, su investigación se centra en simular la formación de galaxias en el universo, tal como lo entendemos a día de hoy, un universo dominado por energía y materia oscura. Hoy nos va a hablar del origen de las galaxias y, sin más, doy paso al profesor White. Gracias.
Muchas gracias, Paco. Señoras y señores, no hablo español. So I'm afraid I will have to speak to you in English. What I want to do today is to tell you a story about the origin of all structure in our universe, how our universe began, and how it came to take the form that we see around us today. So if you like, this is a kind of modern creation myth. So the title of my lecture is The Origin of the Galaxies. So this, I suppose you have seen before. This is our world. This is, until very recently, the only place we had ever been. And not very many of us have ever been anywhere else. It is made on the surface of rock and water. Rock and water are made of atoms. Everything we know, the table, our bodies, the air, is made of atoms. But it turns out that most of the universe is not made of atoms. So this picture was taken from satellites. Satellites circling 100 kilometers above the surface of the Earth with cameras pointing down, taking pictures. You put all the pictures together, you have a mosaic, a map of the surface of the Earth. If you turn the cameras round and look out, you can make a mosaic of the sky. And this is what it looks like. This is the whole sky. This is the Milky Way. The Milky Way is our own galaxy, the galaxy that we live in. It is made of about 10 billion stars. You can see the Milky Way if you go somewhere on a dark night, perhaps not in Madrid. The lights are too bright. But if you go outside Madrid into the mountains on a dark night and you look up, you can easily see the Milky Way crossing the sky. And all the stars you see here, many of them you can see. And even some of the bright stars are quite far away. You can see many of the stars here, the brighter ones, are 10,000 light years away. That means that the light from the star took 10,000 years to reach your eye. So what you see is not the star as it is today, but the star as it was 10,000 years ago, before the beginning of recorded history on Earth. So you are looking directly into the past. Here is another picture of our own Milky Way. This is again the whole sky, and this is at longer wavelengths, infrared wavelengths. So this was made with a special camera in space. And now again you can see the Milky Way here, and you can see better this region, which is the central part of our own galaxy. And this is 30,000 light years away. So what you see in this image is the central part of our own galaxy, not as it is today, but as it was 30,000 years ago, when the Neanderthals were roaming in Europe. You can see, though, much further away. If we go back here, just here, and also here, but look at this one, there's a small splodge, a small patch of light, which is not a single star. If you take this small patch right there, which you can see with your naked eye, if you know where to look, and take a picture, you find it is the Andromeda Nebula. It is another galaxy like our own. So when you look up from the mountains and you see Andromeda, with your own eye, without even a telescope, you are seeing another galaxy. And it is 2 million light years away. So you are seeing back in time 2 million years. So you're seeing back to beginnings of human history, to the time before Homo sapiens took his present form. So you're seeing very far into the past. This is what's called a spiral galaxy, and it's quite similar to our own galaxy. Many galaxies look like this. This is a disk of stars, and it was rotating around the center. So in the previous picture, you have to imagine the sun is here somewhere, out towards the edge, and we're inside this disk. And because we're inside it, it looks very thin. So this is our own galaxy. If you could move out of our galaxy and look down upon it, it would look like this. And it takes the sun 100 million years to go all the way around. But that's only about 1% of the age of the universe. So the galaxy has turned around 100 times in the age of the universe. So that you've now seen 3 galaxies. Our own galaxy, the Andromeda galaxy. Actually, there are 2 small galaxies here. And this one. There are many, many galaxies out there. This is another map of the sky, but every point of light here is a galaxy. In this picture, there are 2 million galaxies. And you can see in every direction on the sky, there are galaxies. But you can also see that in some directions, there are many galaxies. And in other directions, there are few galaxies. The galaxies are arranged in a pattern, which we call the large-scale structure of the universe. So they do not fill space at random, but they like to meet each other in these objects which are called galaxy clusters. So you can think of space being filled with galaxies, but these galaxies are arranged in this pattern. So the most distant galaxy here is 1 billion light years away, 1,000 million light years away. So that means we see that galaxy not as it is today, but as it was 1 billion years ago, before life came out of the oceans on Earth. So we're now looking far back into the past. But we can look even further. This is the deepest optical photograph of the sky that was ever taken. To make this picture, the Hubble Space Telescope pointed in the same direction and exposed for 300 hours. See, I'm used to taking a photograph for 1/30th of a second. This is a camera with a lens 2 meters wide, and it took an exposure of 300 hours. So these are very faint objects. This is a very small patch of the sky. This is a small fraction of the size of the moon. But you can see that even in this small patch of the sky, there are many galaxies. You can see this one is a spiral galaxy, here's a spiral galaxy, here's a spiral galaxy. These are all galaxies. And now we're looking back even further. The most distant galaxies here, which are very faint patches you can barely see, are so far away that the light has been traveling from them to us for most of the age of the universe. So we see them at a time when the whole universe was much younger than it is today. And today, because the universe has continued to grow, those galaxies are 30 billion light years away. So you can see we are now seeing very far back into the past. So the question is, how far can we see? We can see back in time. Can we see to the beginning? Or how close can we see to the beginning? And it turns out that it is possible to see much closer to the beginning. But to do that, you have to look at a different wavelength. And this was first done by this satellite called COBE. It's a NASA satellite, and it flew for 4 years. And it flew above the Earth's atmosphere and looked out away from the Earth. And it observed the sky at microwave wavelengths. So microwaves are light with a wavelength of about 1 millimeter. So that's similar to the waves in a microwave oven that heat your food. And those waves do not penetrate the Earth's atmosphere. So if you want to make a picture of the sky in the microwaves, you have to do this from space. So COBE flew for 4 years. It had 2 instruments which made a picture of the whole sky. One of them was at infrared wavelengths, and I already showed you that picture. That was the picture of our galaxy at infrared wavelengths. The other instrument made a picture of the sky at microwave wavelengths, and a third instrument made a spectrum of the sky, which I will not talk about today. So they observed the picture of the sky for 4 years, and finally we had a picture of what the sky looks like in microwaves, and it was so beautiful that they got the Nobel Prize in 2006 for physics. So let me show you the picture of the sky in microwaves. It looks like this. So the intensity of the sky, the brightness in microwaves, is measured by a temperature. So where there's more microwaves, it's hotter. Where there are fewer microwaves, it's colder. The average temperature of the sky is 2.728 degrees above absolute zero. So this room is 300 degrees above absolute zero. So this is 100 times colder. But it's not zero. And the contrast in this picture is 1/10 of 1 degree. So where it is blue, it is 1/10 of a degree colder. And where it is red, it is 1/10 of a degree hotter. And what you see, if you look closely, is nothing. Why? That is because at this contrast, the sky is the same temperature in all directions. So this is a difference of only 3%, but you still do not see anything. It is very nearly uniform. To see anything, you have to increase the contrast. So let me increase the contrast by a factor of 30. So now, where it is blue, it is 3/1000ths of a degree colder, and where it is red, it is 3/1000ths of a degree hotter. So there's a very slight variation from one side of the sky to the other side of the sky, by 1 part in 1,000. What you can see is there's this smooth variation, and there's something else underneath it. So if you take away the smooth variation, and you increase the contrast by another factor of more than 100, you get this picture. So now the difference between the coldest point here and the hottest point here is 1 part in 100,000. So it is up here, the temperature is very nearly the same, but not exactly the same. There are small differences. So let me explain what has been seen. The pattern here that you see is the reflection of the motion of our galaxy through the universe as a whole. What is happening is in this particular direction where it is hot, that is the direction we are moving towards. The opposite direction, where it is cold, is the direction we are moving away from. And the difference in temperature is what is known as the Doppler effect. It's the same effect that changes the pitch of an ambulance as it passes you. As it comes towards you, the pitch is higher. Dee, 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 dee. And as it passes you and goes away, it lowers. Dee, 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 dee. So because we're going in towards the sky here, the pitch is higher, the wavelength is shorter, and it looks hotter. In the opposite direction we're moving away, it looks colder. So this allows us to measure the speed of our galaxy through the cosmos as a whole. And it's moving in this particular direction at about 600 kilometers per second. through the universe as a whole. So when you take that pattern away, what you see next is this band. This is radiation from material inside our own galaxy. It's radiation from the material between the stars. So this is interesting, but I don't want to talk about it anymore today. What I want to talk about is what you see outside our galaxy, away from where the stars are. And this is structure in what's called the microwave background, which is this radiation itself. So the question is, what is this structure and what are we seeing? And this radiation is the leftover heat from the Big Bang itself. So what we're seeing is structure in the leftover radiation that has come to us from the first instance of creation. So we can ask a number of questions. The first question to ask is, where is the structure? So today, when I arrived, the sun had not yet come out. I thought Spain, the sun always shone. But today in Madrid, the sky was gray. When you look up, the sky is gray, but it's not the same color gray in all directions. Some directions are brighter, some are darker. You see structure in the sky. That structure is structure in the clouds, because the sunlight hits the clouds, is scattered inside the clouds, and then comes directly to us beneath the clouds, because the air under the clouds is transparent. So when you look up, you see the structure in the clouds. The structure we see in the microwaves is exactly the same. Today's universe is transparent to microwaves. So we see back in time to the point where the universe is no longer transparent, and then we see structure in those cosmic clouds. And these clouds are the far edge, the boundary, the limit of the visible universe. And that is because all light is scattered, so we cannot see past them. So everything visible that you can make a picture of must lie in front of these clouds. So this is an image we're seeing of the edge, the boundary of our visible universe. Well, you could say it doesn't look very interesting. What is it we're actually seeing? What is this structure? Well, it turns out at this time, the universe was nearly uniform. It was filled with gas. And what you're seeing is small variations in the density and the temperature of the gas at that time. So that's exactly the same as what you're hearing at the moment. If you took off your headphones and you hear sound going through the air in this room, the sound is small changes in the density and the temperature of the air, small fluctuations. So what we are seeing here is the same phenomenon, but now very far away in space and time in these clouds. These small variations are sound waves propagating through the clouds. So these are weak sound waves in these distant clouds at the far end of the universe. Okay, so I told you that as we look further away, we look back in time. So we can ask, how far back are we seeing? When in cosmic history did these clouds exist? Now, this is really very far back. These clouds are so far away that the universe, which today is 13 billion years old, at the time we are seeing was only 400,000 years old. Okay? So it was nearly 1 million times younger than today. Why do we see so far? Because ever since that time, the universe has been transparent for the microwaves, and they've just been freely traveling to us. At that time, the universe is expanding. So as you go back in time, it was smaller and denser and hotter. So the universe when it was 400,000 years old, was 1,000 times smaller and 1,000 times hotter than today. So as I showed you, today the radiation has a temperature of 2.7 degrees above zero. So then it was 1,000 times hotter. It was 2,700 degrees above zero. So that's about half the temperature of the surface of the sun. So these clouds are actually quite analogous to the surface of the sun. They are gas which has been heated to a temperature where the light won't go through it any longer, and it's about half as hot as the surface of the sun. So we see sound waves. One question then is, when were the sound waves created? So for example, the sound waves that you're hearing in this room are created in my neck. They go into the microphone, they go through the electrical circuits, they go to the loudspeakers, they come through the air, they go in your ears. But the original creation was in my neck. So then what is the process which created these sound waves, which created the structure that we see? And we believe this structure was created a very small fraction of 1 second after the initial explosion. So this structure really comes from very close to the beginning of time. What has this structure become? As I told you, the universe was nearly uniform. These sound waves were the only change, the only variation in structure from one place to another. If the structure had been completely uniform, it would have stayed uniform, and we would not be here. The only reason there is structure today is because these sound waves existed at the beginning. In fact, these sound waves have become all structure in the present universe. So although at this time the universe was very nearly smooth, it had no stars, no galaxies, no objects at all, in fact no elements heavier than helium, these sound waves were still present, and they have turned into everything: the stars, the planets, the galaxies, and the people. So they are the origin of us all. So the next stage in this story comes from another satellite. This was launched about 10 years later, again by NASA, and it was sent to a position called Lagrange point 2. So this is a very special place. You imagine taking a straight line from the center of the sun through the center of the Earth and out the other side past the orbit of the Moon. You come to a special point which has the property that if you put a satellite there, the Earth pulls on it just enough that as the Earth goes around the Sun, the satellite goes around the Sun with it and stays in exactly the same configuration. So the three bodies, the Sun, the Earth, and the satellite, all go around, well, the Sun and the satellite go around the Earth and the satellite go around the Sun together. That's a long way to go. So you ask, why would you send a satellite so far? The point is that we are trying to measure very small differences in temperature on the sky, a tiny fraction, about 1/1,000,000th of a degree. And so to do this, you have to have a very stable temperature gauge. And in particular, you have to keep all sources of heat away from it. So if you put the satellite here, you can put a big sun shield here, and then the instruments lie in the shadow of the Sun, the Earth, and the Moon. They're all behind the sun shield. So as a result, the instruments can look out into space without ever seeing any of these. The Sun is 5,000 degrees. The Earth is 300 degrees. The Moon, 120 degrees. Those are all shielded, so the instrument can look at space, which is only 3 degrees. That allows it to measure the temperatures more precisely. Its map of the microwave sky looks like this. They've used a trick to take away the Milky Way, so you cannot see the Milky Way in the center here. They combine different colors in such a way as to leave the background radiation and take away the material in the Milky Way. And what you can see is they see more structure. That is because the telescope was more sensitive and had better angular resolution. Okay, but you still can't see anything. I mean, how do you understand what is in this map? So we need to interpret the meaning of this structure to find out what it tells us. And it turns out the pattern that we see is influenced by three different aspects of the situation. The first is the geometry of the universe, because that translates angles into the sky to centimeters in the cloud, depending on the geometry and how far things are away. The second thing which affects the pattern is the content of the universe when it was 400,000 years old, because just as the nature of the air influences the sound in this room, so the content of the universe at that time influences the properties of the sound waves. You probably know if you take helium out of a helium balloon and talk, it sounds funny, right? Because the change in the gas changes the sound propagation speeds. So you can use the properties of the sound waves we see to understand what it is that fills the universe at that time. And the third aspect is the process which originally created the sound. So the geometry of the universe is related to whether our universe is infinite or finite, whether its volume is a certain number of cubic kilometers or whether it goes on forever. And this, through Einstein's theory of gravity, is related to whether our universe will last forever, so is eternal, or will eventually come to an end. We believe it had a beginning. It could collapse and have an end and be transitory. This is related to its geometry and its contents. The content of the universe we usually talk about in the fractions of today's universe which are made of different kinds of thing. For example, a small fraction of today's universe is made of light, and most of that is actually the microwaves that we see. Some fraction of the universe is made of ordinary matter, but it turns out that only a small fraction of the universe is made of ordinary matter. Most of it is made of a different kind of matter which does not interact with the light except through gravity. And there's yet another surprise which I'll come to later, that even these three are not enough, that a new kind of energy is needed to fill space. So I will come back to this. And then studying what we learn about the process which created the structure is something about the very first instance of creation. So here we have this map. How are we going to understand this map and understand something about these three things: the geometry, the content, the origin of structure? Well, I think the easiest analogy to this is to imagine this is a universe filled with sound. If you go to a concert hall, you have a room filled with sound when the orchestra is playing. But the sound is not chaotic. When you listen to an orchestra, you can tell the difference between the different instruments. And that's because your ear can separate the sound into the different frequencies. And different instruments have different strengths at different frequencies, and that allows you to recognize a violin or a flute or a double bass. So we can do the same thing with the cosmic sound. And so this is a picture of the sound content of that image, where we split it up according to how loud the different wavelengths are. So this is wavelength. So this is the long wavelengths. This is the deep sound. This is the double basses. These are the short wavelengths. That's the high-frequency sound. This is the violins and the piccolo. And then this is how loud the instrument is playing. So high is very loud, low is not so loud. You see, 0 is here, so there is sound at all the wavelengths. And then the points are the measurements from that map. So what you see is that somewhere in the middle, the violas are playing very loudly. So the double basses are playing, but fairly quietly. The violas are playing loudly, the violins and the piccolos less. Okay. So the measurement then of the points. The red line is a theoretical prediction for what this should look like based on these three things: the geometry, the content, and the original origin of structure. So what we've learned from this is that the geometry of the universe is the simple geometry we learn in school, where the angles of triangles always add up to 180 degrees, and where parallel lines never meet, the geometry of Euclid. So our universe apparently has a geometry which obeys Euclid's laws, which technically means it's flat. For example, if you take the surface of the Earth, it's spherical, it's not flat. And if you make a triangle on the surface of the Earth, the sum of the angles does not add up to 180 degrees, it's bigger. So that's because it's curved. But the universe as a whole in 3 dimensions is not curved, it's flat. It turns out that the material in the clouds which actually interacts with the light, like ordinary matter, is only a small fraction, only about 4% of the content of today's universe. Much more is made up of matter which has gravity, but does not interact with the light except by gravity. And this is what astronomers call dark matter. And this is something which astronomers have known about for almost a century, that the ordinary material that makes up the stars and the planets is not all the material that is out there. And a particularly striking example where you can see the effects of this are here. So these are galaxies in a galaxy cluster, and you can see these strange objects here, and here, and here, here. So these are also galaxies, but they are galaxies which are behind the cluster. And what is happening is as the light from those galaxies comes to us, it has to pass through the cluster. And so as it goes through the cluster, it feels the effects of the gravity of all the material in the cluster, and this bends the light like a lens. So the cluster is acting as a lens which is making an image of the galaxies behind it. And it's a very bad lens. So this galaxy is seen 4 times. One, I can hold it steady enough. One here, one here, one here, and over here. So you actually see the same galaxy 4 times. There are 4 different light paths from the galaxy which come to us because of the effects of the gravity. And because of this, we can work out how strong the gravity must be in this region. And what you find is that the total amount of material in this region has to be about 50 times as much as the mass in all the stars. So somehow in this region, there are many stars inside these galaxies, but there's much more of something else that we do not see. And so this is how astronomers had already discovered dark matter before we found the need for it in the microwave background. The most puzzling thing, which was discovered from this, which I'm not going to spend much time on today, is that this is still not enough. We have 4% here, 20% here. This is still only 1/4. The rest, maybe 3/4 of the total energy in today's universe is in something else, which we now call dark energy. And this was first demonstrated by a different phenomenon, which is that it actually causes the expansion of the universe today to get faster with time, to accelerate. So the possibility of such a kind of energy was actually understood by Einstein in his theory of gravity in 1916. And he actually made a model for the universe which had such energy in it. When he discovered later, in the 1920s, that the universe was expanding, he thought it was not necessary and thought this was a mistake. But he'd nevertheless seen it was a possibility. Now, in the 1990s, people discovered that our universe apparently does have this kind of dark energy in it, and they found it from this kind of plot, which I won't spend much time on, but what is shown here is the brightness on the sky of an exploding star called a supernova. And if it's close to us, it looks bright. If it's far away from us, it looks faint. So this is how bright it looks. So the ones at the bottom of the plot here are close to us, they look bright. The ones at the top of the plot are far away, they look faint. And then the horizontal axis is how fast the supernova is moving away from us. So here, they're moving away from us slowly. Here, they're moving away from us very fast. So what you see here, for the supernovae which are quite bright and fairly nearby, is a straight line. And this is just the expansion of the universe. If the supernova is twice as far away, it looks 4 times fainter, and it's moving away from us twice as fast. So this is the expansion of the universe. When you go to very faint supernovae, they are so far away that light has taken most of the age of the universe to get to us. So when the light left the supernova, the universe was younger, and it was not expanding at the same speed. So this is no longer exactly a straight line. And by looking at the change from a straight line, you can measure how the expansion of the universe has changed. And the surprise was that the distant exploding stars, the distant supernovae, are fainter than expected, which turns out to mean that the universe is expanding faster today than it was in the past. So everyone had expected that gravity would gradually slow things down. So the universe expansion would get slower with time. And this indeed did happen for most of cosmic history. But recently, it has started to expand more quickly again. And this is something which is predicted also by the dark energy, which we need also to explain the microwave background. So that's for the geometry and the content. Now, what was the process which produced the structure? It looks, the properties that we see on the sky are those that are predicted if all the sound waves are a consequence of quantum fluctuations of the vacuum. So in quantum mechanics, the theory of elementary particles and very small objects, the vacuum is not dead, but is filled with particles which are continually being created and dying on a very short time scales. So the vacuum, in a sense, is not really empty. It has a life. And the structure of the vacuum is understood in the lab on very small scales. And the properties of such quantum fluctuations are understood. And the properties we see on the sky, the statistical properties, are those that are expected if the structure arose from quantum fluctuations of the vacuum very close to the Big Bang. Perhaps 10 to the minus 30 seconds. That's 1 over 1 with 30 zeros. Seconds after the Big Bang. So if that's the case, then everything has formed from the vacuum, this particular vacuum, because the fluctuations we see in the microwave background were created from these vacuum fluctuations, and we have grown from the fluctuations we see in the microwave background. So everything has come from the vacuum, so everything has come from nothing. So the last story here was another satellite. This was the third stage. It was a European satellite called Planck, which was launched in French Guiana in 2009. When we first started working on this project, it was in 1994. So it took 15 years to get things before you could finally put it on the top of this rocket, this Ariane 5, and launch it. So when you go to watch these things, you are not allowed to go close to the rocket. You have to stand at least 2 kilometers away. So what you see looks more or less like this. But nevertheless, the Earth shakes. And you can hear the noise. And then very slowly, it starts to go up. And you see 15 years of work sitting on top of this exploding thing. And it goes up, and it goes up, and it goes up, and it goes up, and then it does that. And if you haven't seen this before, you get a bad feeling in your stomach when this happens. But it turns out this is just a perspective effect. Because as it goes up, and then you're looking along it, and then it turns over with to counteract the motion of the Earth, the rotation of the Earth. And so this is just a perspective effect. The launch was perfect. So it also went to L2, and then it observed the sky. So it had a telescope. There was a big mirror here, a smaller mirror here, and the instruments are all in here. And then it rotated, and it looks like this. So the telescope rotates, so you see the primary and secondary mirrors. And the Earth is off in this direction. So as it rotates, then the direction it's looking makes a circle on the sky. But now, as the Earth goes around the Sun, the satellite goes around with it, and the rotation axis gradually changes. So you can see that if you wait 6 months, this circle has covered the whole sky. So then you've made a map of the whole sky. I'll let it finish because ESA made a nice effect at the end of the movie. So here we are 6 months after start. We've gone halfway around the Sun, and we have a picture of the whole sky. So now we can make a map of the microwave sky, and then we can compare our map with other maps of the sky. Let's see what we found. In fact, Planck made 9 maps, 9 different colors. Each of us a different frequency. This is 30 gigahertz. This is 900. So this is a factor of 30 in frequency or wavelength. And what you can see is in most of these maps, you can see the structure in the microwave background very easily. So the colors here are such that the microwave background should look the same. So if you look here, you can see exactly the same things here and here and here. But having the different frequencies allows you to subtract the effects of this stuff, which is in the foreground in our own galaxy. Because you can see you can use these maps where the galaxy is very strong to correct these maps where it's weak. So this allows you to make a map where you only see the microwave background, which then looks like this. So this is an extraordinary image because this is an image of the boundary of the visible universe, of the entire boundary, because it's the whole sky. What's more, now with Planck, the precision is so high that in fact it's essentially a perfect map. If you make a better satellite, you won't get a better map because it's already measured everything there is to measure. So we've now seen our past. You can compare Planck and W maps. So this is half of the sky, this is the W map image, this half of the sky is the Planck image. And if you take this little square, this is what it looked like with W map, this is what it looked like with Planck. If you look carefully, everything you see here, you also see here. So WMAP had already made a very good map. It's just that Planck sees more detail, but it has better resolution. So if we now look at the sound content of the clouds according to Planck, these are the measurements, the red points, and you can see here are the violas and the violins, but now we have even higher instruments. And you can see that these are very well measured, and this is the theoretical prediction. It still goes through all the points. It goes through all these different ups and downs, essentially perfectly. So it really does look as though we understand very well what has created these sound waves. So if we compare what happened, well, actually WMAP already had very good results. So if you compare before Planck, this is WMAP, and after Planck, the fractions of the different things changed a little bit, but not very much. And the universe is still flat, but now much more accurately measured than was possible with WMAP. It turned out from Planck we could see that the expansion of today's universe is a bit slower than people had thought. So this made the universe suddenly 80 million years older. But that's only 80 million out of 13 billion, so it's not so much. And perhaps the most interesting thing were the results now with this much higher precision strongly support the idea that all the structure did indeed originate in this very early vacuum. So that is, we can see what the universe looked like at the beginning. We can ask, do we understand how today's universe evolved over the next period from this very early time when everything was nearly uniform to today? So here's another picture of today's universe. We are here in the center. This is 1.5 billion light years. And every point in this picture is a galaxy. And this is distance away from us. So these are two thin strips on the sky, and the astronomers have measured the distance to every galaxy in the strip and then just made a plot. And so what you see here is the large-scale structure of the universe. So where there are many galaxies, these are the galaxy clusters, and there are these regions which have very few galaxies. And remember, every point in this plot is actually a galaxy looking like one of these, or our own galaxy. So all this structure had somehow to emerge from these sound waves. So it took the universe 13.7 billion years to do this. But as you know, in a computer you can do many things which you can't do in real life. In a computer you can be invincible, and you can destroy thousands of invading aliens before dinner. So in a computer you can also create the universe much more quickly than the real universe did. And how do we do this? We want to understand how the universe started smooth and came to have the structure we see. We want to understand the origin of the particular structures that we see around us. So the idea is inside the computer to follow the material in some region of the universe. For example, a cube which expands with the universe. So at the beginning of our computer calculation, we put everything inside the cube to be very nearly smooth and to have only small deviations from smoothness which are the same, that match those that we see on the sky in the microwave background. So we start 400,000 years after Big Bang with the initial conditions for our calculation which correspond to what we see on the sky. And then we program the computer to follow the laws of physics. And the most important is the laws of gravity. And then we ask it to calculate what happens. And so the computer calculates forwards in time. And if we understand things and that we've programmed the computer correctly, after 13.7 billion virtual years inside the computer, we should end up with something which looks like today's universe. So let me show you some videos to show you how well this works. So let's imagine you take a cube, it's expanding, and you cut a thin slice in it, and you look and see what happens. So that's what this first video shows. So here we're close to the beginning. So this picture is expanding with the universe. So you do not see the expansion. But we're starting quite early, so the structure is nearly smooth. This is later than the microwave background, but still before any strong structures form. Now, watch what happens as time passes. Gravity gradually pulls things together and makes objects. So you can see these regions are becoming emptier and emptier, and these regions are becoming denser and denser. And so you can see the material flowing along these regions to make bigger and bigger objects. And the object in the middle here would correspond to a cluster of galaxies. So this is the evolution of the universe inside the computer, so the virtual universe. And you're just looking at the dark matter. because that was the easiest part to calculate. So when you get to the end of a simulation like this, if you look at it for a very large region, then on large scales it looks very smooth. So this is a large fraction of the distance to the other side of the universe. But if you zoom in, you gradually see more and more structure. So here now you can see a pattern which is starting to look like the pattern we saw in the image of the galaxies. If we keep zooming, we can zoom inside this object. So this is now a single object which would correspond to a cluster of galaxies like the one which I showed you with the gravitational lenses. And you see inside the cluster there's dark matter. There's a big concentration at the center, and there are many, many lumps of dark matter, and these would correspond to the galaxies. So perhaps the best way to appreciate the structure is just to fly through it. So now you take a virtual spaceship inside the computer and you fly through your virtual universe. So there are several advantages in doing things in the virtual universe. The first advantage is that you can go very fast. So we're flying here at 10 to the power 14, 10 power 14 times the speed of light. So this means we cross the whole universe in 2 minutes. So that helps. The other thing that's very helpful is inside the computer we can see the dark matter. In the real universe it's dark. We can only see the galaxies. So what you're seeing here is the structure in the dark matter. And in fact, in this simulation, it simulated only the dark matter. So I can claim it looks good because the simulation calculated the things we cannot see and left out the things we can see. So we have a picture of the dark universe, the distribution of the dark matter. To compare with the real world, we have to follow the ordinary matter. We have to understand how the galaxies form and turn into stars inside all these lumps of dark matter. We can do this, but we cannot do it as accurately as we can calculate the dark matter. Nevertheless, if we try, we can make a picture of the light. So here's the dark matter. This is a prediction inside the computer for where the galaxies should be. So now, inside our computer, we have a full virtual universe full of galaxies. So I can send my real graduate student into the computer with a virtual telescope and ask him or her to make a survey of the virtual sky exactly the same as the real survey of the real sky. And then we can compare whether the virtual universe looks the same or different than the real universe. And that's what's been done here. So this is half of the picture I showed you before of the real sky with all the galaxies. There are about 50,000 galaxies here. And these are other surveys of regions which have been expanded, so at a different scale. So these are then the virtual universes, the pictures made inside the computer by the graduate student to compare. So the question is whether the structure here inside the computer looks like the structure in the real universe. If it does, then we have understood quite well how the present universe evolved from the sound waves. So you compare this one with this one, this one with this one, this one with this one. So, looks similar. So the real test is to take some universes. So here, a 6, 5 of them came from the computer, and 1 is the real universe. Okay, so who can tell me which is the real universe? So if you can't tell the difference, I claim this means that the computer did a good job. And remember, what the computer did was take the sound waves we see in the microwave background, assume only the law of gravity and the laws of physics, and calculate what the universe should look like. And apparently, we came up with something which looks very similar to the real universe. So what I think I've told you is that our universe was born about nearly 14 billion years ago in a hot and almost uniform explosion. And we know that it was hot and uniform because we can see it. When we see the microwave background, we actually see the universe when it was only 400,000 years old, and it was nearly uniform, and it was hot. So this isn't a theory, that's what we see. Of course, we can't see behind the clouds. We think that if we went even further back, everything came from a big explosion. That's called the Big Bang. Now, the structure we see in the clouds has the properties we'd expect if it grew from quantum fluctuations of the vacuum itself at some very early time. So this is a hypothesis because we cannot see the earlier time. But what we can do is measure accurately and see if the structure corresponds. And so far, the correspondence is good. So it appears that everything formed from nothing, although the nothing is in quotes because a vacuum in quantum mechanics is not really empty. However, only about 5% of today's universe is made of ordinary atomic matter. More than a quarter appears to be made of some other kind of matter, which cannot be any of the elementary particles we already know. They are already excluded. So if it is an elementary particle, it will need to be a new kind of elementary particle. And so one of the big tasks for physics and astronomy is to see if we can find some other way to demonstrate the existence of this particle, other than just its gravitational effects on the sky. And then about 2/3 seems to consist of dark energy. And here we know that it is accelerating the expansion of the universe today, but otherwise we know almost nothing about it. However, what does seem to be the case is all the structure of our present universe, the galaxies, the galaxy clusters, the stars, the planets, and the people formed out of these weak sound waves that we see in the microwave background, and they formed primarily through the effects of gravity. So in this sense, we are all sons and daughters of gravity. Thank you.